So thank you everyone for coming. It's great to be here and to connect with you all. I'm going to be talking today on quantitative imaging and AI. My name is Chung. I'm Vice President and Chief Data Officer at MD Anderson, have a computational imaging lab, and I've been involved with KIBA, the Quantitative Imaging Biomarker Alliance of RSNA, for a number of years. And we've now, much like a lot of the field of radiology, we're recognizing the need to address AI within our portfolio and how do we actually partner with that. And so we've got two hashtags for those of you who are on Twitter, the hashtag QI for AI and hashtag AI for QI, and I'll walk through the thinking behind both of these. So this was AI in RSNA 2019. There was a whole other floor for AI companies, made a big splash at RSNA. AI is here, and after a hiatus with the pandemic, you can see here there's new players who have grown, other players that have merged, and so this is an evolving environment, and yet we really are struggling. And there was just a recent panel discussion around why is it so hard to actually translate this into the clinic and actually impact our patients in a more meaningful way than all of the efforts that are being put in. So if we take a step back and look at the clinical imaging workflow, you can see that the images are acquired, they're pre-processed, images are collected. We want to get the image-based tasks and the reporting and integrated diagnostics incorporated. And currently what happens, and you just heard from the last speaker around the burden and potential burnout that this is causing as the volumes go up, is that human inference is incredibly powerful. And so how is it that we can actually get images off of Canon and Siemens and GE and all these different vendors, and yet the reports can be generated and the images can be interpreted? It's because the human inference is so powerful. There's a lot of nuance and understanding that's incorporated into that radiology report. The idea of integrated diagnostics, the fact that the radiologist takes the time and goes into the chart, incorporates that known knowledge, incorporates the reason why that image was even ordered, quite frankly, is integrated into that radiology report as the images are interpreted. Now, as AI is reaching into the entire imaging workflow, machines don't have human inference, at least not today. We could speculate on whether that will actually get there. But this is actually driving a new need for what and how data is generated and flowed, because the things that we take for granted as we gather those images, things that we take for granted in terms of how do we interpret that, even though the nuanced images are acquired differently, the protocols are slightly different, the scanners are a different date and different version, that's not so obvious to the machines, and it may be influencing how successful we are in developing our AI algorithms, as well as successfully deploying and maintaining those algorithms over time. And when you think about what that means, when you take a step back and look at the quantitative imaging process of precision medicine, there's a lot of common needs to what AI is requiring of us today. When we look at image acquisition, image post-processing, these are all the steps I went through earlier, perhaps image registration over time, segmenting that region of interest that we want to extract those features, and relating those out to the clinical outcomes, whether it be tumor response in oncology, clinical outcomes overall, or even relating it to the genomics. Variability in each and every one of these blue boxes introduces a challenge in terms of the clinical interpretation. It introduces technical noise when we're really trying to find the biological signal. And so, much like what we're talking about in quantitative imaging for precision medicine, variability in each of these little blue boxes, they're actually big blue boxes, will actually influence potentially how well we can actually train the algorithm, deploy the algorithm, and maintain that algorithm, because all of those upstream variations will introduce uncertainty and the utility of those AI models. And at the same time, if you look at those blue boxes, you can actually say that AI could potentially be used to apply and assist at each of these steps to harmonize, standardize, and allow that data to flow through. Hence the hashtag QI for AI and AI for QI. And radiological imaging, I work at MD Anderson Cancer Center, so I gave a cancer example. imaging overall for cancer treatment has really become a beacon. And we started with sort of, if you think about films, standard films could be like the roadmap that you used to turn pages through as you went on a road trip. Then GPS came around and you had some 3D information, but we actually want to have that anticipatory signal where your phone is pinging you saying you need to leave for your meeting now or you're going to get stuck in rush hour traffic to get there on time. And we are getting there in terms of what we are capable of achieving. There are signals. We can use AI to signal saying you should look in this area of the image, like in the breast image you can see on the left. There are ways to characterize these tumors or lesions further with advanced imaging. There's ways we can actually anticipate and predict and model out how the tumor is going to behave with differences in treatment. And having said that, there are challenges in terms of addressing that noise. At MD Anderson, what we've done is taken this and created it as an institutional initiative called the Tumor Measurement Initiative. We kept it vague on purpose because measurement can mean measuring the size of the tumor all the way out to characterizing components of that tumor. And we've taken a step back and taken a data science approach in terms of looking at standardized data collection. So standardizing that as much as we can, looking at the QA and QC of those images as they're coming in, before they come in to the data scientists who are developing out tools to automate segmentation, automate extraction of features, and then also being real with ourselves, knowing that there are limitations in the annotations that we actually provide and that radiologists provide in how we're actually interpreting the margins of that tumor or region of interest. And so looking at imaging pathology correlation, relating it to imaging outcomes of local therapies. And we want to build out these tools that can actually be used in the research space, validated, monitored, and the life cycle of those tools tracked for clinical implementation. And clinical implementation meaning for true clinical use over time. And overall, over that period of time, we're working on developing an automated, standardized measurement for every tumor in every patient at every time point. That measurement will evolve over time. It could start with volume, it could get to very specific metrics, but if we don't actually take this standardization approach and pipelining of the data flowing through, we'll always be challenged with the technical noise versus the biological signal. And so I'm going to take a step back and think about where AI has come from. It's come from the Internet of Things, computer scientists showing that we can actually categorize, labeling a cat in an image. And yet, even within these simple flat images, you see that when you look at the numbers, the 0.99, these are softmax outputs for softmax units for the correct class and how confident you are. The closer you are to 1, the more confident you are. The lower the number and closer to 0, the less confident you are. You can see, regardless of which model you use, the confidence goes down as the image quality deteriorates. And similar things are happening in the radiological image. Are we measuring image quality today? Not consistently in any shape or form. And so we need to start to think about how are we going to do this and the need to do this, because the confidence of those models will depend on the quality of the image. The second piece is, when we think about labeling and looking whether the image, whether the model has performed or not performed, when you look at this box, you can see that the solid box is what the model had actually selected out as the person, but the dotted box is the corrected annotation saying, well, you're missing the legs of the lady. Most of us will know that the legs are there. Perhaps if you're going really fast, you may miss it. But when you actually think about a tumor and saying, did this actually segment out the whole tumor, that border of that tumor can be very variable to the different observer. And so how do we actually truly find ground truth? And so these are part of the challenges of just translating models that work to label cats over to modeling tumors. The second piece is that you can see the trees from the forest, so you can see all the different chairs and you may miss things. And so if you train a model in these lungs on the left that look quite clear other than the one lesion, and the model is successful, and then you try to apply it to a patient that looks like this image D on the right, you can see why the model is not going to appropriately perform, or perform as you expect it to based on the statistics that were published. So there's been a growing realization for the need for quantitative imaging to help us start to standardize the imaging. Those examples I've given are very patient-specific, and I'll get to that in a moment. But even from the images themselves, if you think about artifacts being in there, potentially being misclassified or mislabeled, we are starting to realize in the neuro-oncology community, there's been a lot of work across disciplines to really say we need to start to acquire images more consistently, but also setting realistic boundaries of what's the ideal, what is acceptable, what is the minimum acceptable sort of imaging protocol, to say that we can actually confidently measure tumor in these images. And within the Quantitative Imaging Biomarker Alliance, there's been a lot of work around standardizing the pipeline of image acquisition. What is the QA and QC that's needed? How do we actually process those images out to extract these quantitative parameters? So there's now a growing realization that we need to grow as a community and connect through the community, and this is another big effort that the Kiba organization has really realized and is wanting to connect out with the different clinical groups. And so if you're involved in any of those clinical groups, we'd love to hear more. And so when we think about quantitative imaging for AI, it means that the quantitative imaging itself can enhance that AI development, accelerate how quickly these models learn, and also enable that clinical deployment in a safe fashion and a reliable fashion. And the second piece is that the hashtag AI for QI is using that AI and building out tools that can help improve and enable clinical implementation of quantitative imaging itself. Now, one of the challenges that we have is that there is a lack of awareness of this so-called AI chasm, and this is true for most technology, that there are the innovators that are very early, starting to invent these things and starting to show proof of principle that it works. There's the early adopters who are starting to learn, and they usually get way into the weeds to understand that technology. And then there's the gap to get to the main majority of people utilizing it. And there's a gap in terms of time investment, learning, education, and that's the chasm. And one of the things that has resulted is this chasm has resulted in a slowness of scientifically sound algorithms and its use cases that are published being translated and applied in meaningful real-world applications. And one of the things that I would argue that's creating this chasm is a contextual bridge. So the context itself around how the images were acquired, understanding those technical limitations, is a critical bridge to realizing the impact and value of applying these AI models, where we can actually safely apply these models and the data science tools in the real world settings. And I'm not alone. There's a lot of publications that are growing around this metadata construct around the fact that this metadata, which are the descriptors around how that data was acquired. So when you think about imaging, this metadata includes things like all of your DICOM headers in terms of what your pulse sequence looks like, what kind of contrast did you use if you used contrast, how was that injected. All of those pieces will enable the transparency for the reproducibility of AI models, because if you've acquired your images in a very different way, that might explain why this model is not working for you. And we're not necessarily taking that step to actually gather that metadata before we just apply. We say we're going to use federated learning. We take a model, we throw it into a new environment, and we say, oh, we need to retrain. And perhaps that is not the order we need to do this in. Perhaps we need to look at that metadata. And there's a paper that I published back in December 2021 around how cancer needs a robust metadata supply chain to realize the promise of artificial intelligence. Andrew Ng has recently also published on the idea of unbiggen AI. So rather than just taking everything out there, making AI data hungry, perhaps it's time for us to really think through smart-sized, collecting that metadata, knowing what we're actually dealing with in that data set, data-centric solutions to this big issue. So what does it mean to build meaningful training, validation, test data sets? It means integrating that metadata to help us. The metadata, those descriptors, will inform the context around which these models are being developed, validated, and deployed. So some context, as examples, that may introduce bias. So a cohort selection of age, and this was shown during the pandemic. We saw that there were hundreds of AI models that were developed using a large repository of data of COVID images, COVID chest images, trying to diagnose COVID out of those images. What happened was it was very early on in the pandemic, and a large proportion of the normal lungs were actually pediatric lungs. Age was not necessarily considered by all the people who were developing hundreds of these algorithms. And so what happened was the AI models were actually learning the difference between a pediatric lung, which was normal, and an adult lung, which had COVID. Now you go and throw that algorithm and try to show it a bunch of adult lungs, and it couldn't diagnose COVID because it had not learned to diagnose COVID. It had learned to diagnose the difference between a pediatric and adult lung. Great example of how age in that context was really relevant in terms of how we build out our cohorts based on how we want to use the tool. So thinking about what is that application before we start building out the model. Other things that could similarly influence your model performance include race and ethnicity. There could be differences. There's been a lot of examples in terms of skin imaging and skin color. That's one example. There could be other nuances in terms of bone density in different ethnic groups. SES, and so the frequency with which someone can come into the hospital can be influenced by your socioeconomic status, and so you may not have insurance to come in all the time, so you're going to have different measures in your AI models than someone who may have more frequent measurements. Geographic location, is there an environmental association, diet, comorbidities in terms of other comorbidities that could be influencing, and so often we don't know exactly what the model is looking at, and so if you have other comorbidities in your patients and you're not balancing those out, your model may be learning other nuances that you're not wanting the model necessarily to learn. So considering these as you build out your cohorts is really important in terms of making sure that it's applicable in the broad sense. In the cancer setting, and I'm sure many other genomic diseases, there's classification, stage, how advanced is that person in that particular disease priority, and does the AI model get influenced by that? For instance, if there's a ton of plaques from MS versus not, that could influence your model performance. If there's lung disease behind a lung cancer and there's a lot of sort of dense ground glass changes in your lungs relative to a tumor, it may not diagnose that tumor as avidly as someone who has a completely clear lung. So thinking about those comorbidities as well as the stage of disease is really important. And finally, going back to the Kiba story, there is measurement error bias. So if you don't train your model across multiple scanners, or if you do train across one scanner and you try to apply it to other scanners, these can create limitations. Similarly with protocols, similarly with patient cooperation. So did the patient get sedation and you're doing a neuro exam, that could actually influence what you're actually finding in your neuroimaging fMRI studies. And so thinking through those nuances around what that cohort represents as you're building your models will allow you to actually help you deploy those models in a broader sense. Now, finally, I'll end here in terms of the model performance and what we define as success. Historically, over time, we've really focused on the holistic generalizable model, that it should work across all circumstances. But if we really think and pause and think about all the different scenarios in which this model could be deployed, and now we're trying to, it's kind of like getting a consensus statement in many ways, is that it's a giant compromise, right? So you're not going to get perfection in any one of those settings if you're trying to make it work in all of those settings. And so perhaps I will tease those who are developing models out there is that perhaps we need to account for the biases. We need to account for the fact that there are differences in opinion, there's interoperability differences, practice differences, as well as differences in the data themselves that impact model performance. And these biases that are often revealed in that metadata, the descriptions around the data, may actually give us the reasons why the model is failing. And so rather than taking a pure federated approach that we commonly think about of, let's just try the model, let's retrain the model, perhaps we need to pause and say, why did that model fail, and can we actually correct for it? And so really thinking through, is this model being applied in the right setting? And I give this bunch of cars here, because I like cars, but it's also just to show you that there are many different vehicles that we call cars or automobiles in many different ways. And there are places and settings where you're going to use them. So you're not going to take this F1 race car and drive it over the rocks that this SUV is driving, right? And so you're not going to take a minivan and try to park it into that spot where the smart car is sitting. And you won't take a family of 7 into the smart cars. There is a time and place for each of these things. And similarly, I would argue perhaps we should be thinking about models in a very similar way. I'm going to summarize by saying that the quantitative imaging for AI development and enabling these clinical implementation, really, we want to start with thinking about precision medicine and knowing that precision medicine starts with that precision measurement. And the radiological images are rich with measurements, but standardization is critical to developing effective tools with great promise of AI-enabled tools to extract these measurements in the clinical setting and allow us to approach this in a scalable way. Quantitative imaging can facilitate the development and successful clinical implementation of AI, accelerate that perhaps, and enable precision measurements moving forward. And vice versa, the hashtag AI for QI, using AI to help improve and enable clinical implementation of quantitative imaging is something that we're definitely interested in. And I think that we need to allow this to be scalable. And the AI itself can actually influence our current quantitative imaging measures. So as we implement things like accelerated acquisitions, when we apply AI, we don't know that those images can actually be applied in the same way and rigor to the quantitative imaging biomarker profiles that we have at Kiva. And so evaluating this for safe deployment and making sure that when we say it's Kiva compliant, we know that it will perform in the same way is another component in terms of the hashtag AI for QI. So I'll end there and thank you. There is a Kiva symposium. There's a quantitative imaging symposium that later this week. Please pay attention to it and come back and hear more about that and see how you can get involved. Thank you.